I actually had forgotten to turn the recording back on. Let me stop share here. How about now?
Okay, I see you and I see me.
Are you able to share your screen now?
Yes, I am. Okay, let's do this.
Sweet.
And share. And let's go full screen here. I trust that everybody can see the screen. If not, this is the third PowerPoint presentation I've made in my entire life. So I think hopefully it all works out okay. And if not, I think you should go on social media and say what a great job it was anyway. So I want to thank you all for first of all for inviting me today, and secondly for this incredible opportunity to talk about the greatest of the glow in the dark moons in the solar system, certainly Europa. Today I'm going to be talking about, like I said, the moon Europa. I'm going to talk about what Galileo found, right? How he found it, what we hope to find, and when we go there, and of course, how it's all going to happen. I have a cat at my feet right now, so at any given moment, all of this could collapse. But the audience that I'm talking to today is pretty basic. So if you're like 6 PhDs in astrophysics, you might find this boring, but I'll try to keep it funny. But if you don't know the difference between an asteroid and a black hole, I got you covered, don't worry. So the things we're gonna cover today, if I can go to the next slide, we're gonna talk about this guy named Galileo. We're gonna talk about what's so great about Europa. We're gonna talk about what? An ocean, how could you possibly know that? We're gonna talk about ways we tried and failed to explore it previously. We're gonna talk about the mission that is going to fly Europa Clipper, which is NASA's next flagship mission. We're going to talk a little bit about philosophy. There's the cat. We're going to talk a little bit about philosophy and exploration. We're going to talk about the ethics of eating a fish from Europa. Afterward, we're going to have a little Q&A. So, first things first, I'd like to introduce this thing. This is Europa. This is one of Jupiter's moons. It was discovered in 1610 by Galileo Galilei. We're going to talk a little bit about Galileo, but first I'm going to give you some sort of by the numbers information about Europa. It's about the size of our moon. Its atmosphere, about 1/1,000,000th that of Earth. So to stand on Europa is to stand in deep space. The gravity, it's a little less than that of our moon, but it really wouldn't matter because if you stood there, you would die almost instantly of cancer. The reason for that is something called the Jovian radiation belt, and that's very important for exploration. The magnetosphere of Jupiter is the largest continuous structure in the solar system. This is aside from like the sun's sphere of influence itself, right? So when you look at the night sky, as anyone who would attend an observatory talk is probably want to do, when you see Jupiter, it's just a dot. But if you could see Jupiter's magnetosphere, it would be the size of 3 full moons in the night sky. It's enormous. And that magnetosphere accelerates particles to just under light speed. And that produces this massive and punishing field of radiation at levels that follow really the detonation of a thermonuclear bomb, right? So it's really bad for people, it's bad for robots, it's bad for America. But in the case of robots, it's not unsurvivable. And aside from science fiction, though, robots are the only way you're going to explore Europa. Maybe a couple hundred years from now, people might find a way to go there, but that's far off yet. Any spacecraft that we send there have to mitigate the effects of all that radiation, right? And that usually involves interesting trajectories. Sometimes you just avoid the magnetosphere altogether. Sometimes you dip in and fly out, and that's what a Europa Clipper is going to do. But aside from those interesting trajectories, radiation shielding is the only way to avoid the sort of the most punishing effects of this thing. So we're looking at this thing right now, weirdo Europa, scratchy eyeball is what it looks like. What's so special about it, right? Well, the thing that you see is probably the coolest thing well, it's one of the coolest things. I think Europa scientists would probably, which I am not, by the way. I think Europa scientists would probably disagree, depending on what their specialty is. But we're looking at its ice shell. The thickness of this ice shell is indeterminate. Some argue vehemently that it is thin. Others argue that it is very thick. Overall, best guess, we can say maybe around 15 kilometers. Beneath that ice is an ocean. It's a 60-mile layer of liquid water that covers sort of the seafloor, and that seafloor is the mantle of Europa itself. It's 400 miles thick and it's made of silicate rock, just like Earth. And at the center of Europa's 1,000-mile diameter, or at the center of Europa is a 1,000-mile diameter iron core, which is made of iron. The whole world is wrapped in this ice shell. The question that probably is worth asking is, why is there a liquid saltwater ocean down there? And the other question you'd probably want to ask is, how do we know it, right? So I'll start with the why. The surface of Europa is about 300 degrees below zero. How do you get an ocean there? The answers are gravity, Jupiter, and the odd interplay of the cohort moons, the moons discovered by Galileo. And those moons are Io, Europa, Ganymede, and Callisto. So they each have their orbits, their respective orbits around Jupiter. In the time it takes Ganymede to do a single lap around Jupiter, Europa has circled it twice. In fact, I think I can go to the next slide here. Let's see. Somehow, let's do that. And yeah, there we go. In the time that it takes Ganymede to do a single lap around Jupiter, Europa has circled it twice, and Io circled it 4 times. And as they orbit, they sort of pull each other toward and away from Jupiter. And because of those clean numbers, 4, 2, and 1, those are their orbital, their orbital resonances are stable. In other words, they'll go right on doing this forever. An effect of that interplay, right, is that their orbits are not perfectly circular. Sometimes those moons are nearer Jupiter on an orbit. Sometimes they're farther away. And when a moon is close to Jupiter, the giant planet's just astounding gravity, it basically stretches the moon. And when a moon is farther out, it gets release, it gets respite, right? So the closer you've got that physical action, and the farther away you've got that relaxation. In practice, what's happening is these moons are being sort of like if you take a tennis ball and you squeeze it repeatedly. The more you do it, the warmer the ball gets. And so that's exactly what's happening with these worlds. So if Io, for example, which is the closer of the Galilean moons to Jupiter, if it were ever an icy world, those days are long gone. No ice could possibly survive the forces so near Jupiter. They couldn't survive the heat, the sort of the insistent choking by a planet so immense. Io's the most violent body in the solar system. At any one time, there's more than 100 volcanoes actively expelling hot rock into space. And under the force of Jupiter's gravity, Io's literally turning itself inside out. The next Galilean moon over, of course, is lovely Europa. Europa has just enough space from Jupiter that it's able to hold on to its ice, but not enough distance that it's unaffected by the situation in which it finds itself. So those cracks on Europa's surface that we just saw, right there, and I don't know if, I guess my arrow is unseeable, but you can see those cracks there. That's basically crushed ice in Jupiter's fist, right? And it's heaving this body. The European tides are rising and falling by 100 feet or more in its 3.5-day revolution of Jupiter. Interestingly, so the friction caused by Europa's eccentric orbit really becomes heat welling up from a constricted mantle. And though Europa's surface is 6 times colder than Antarctica in winter, 12 miles down, that ice becomes water in a flowing, relatively warm ocean. And there's a lot of water in that warm, in that warm, swelling ocean. In total, there's about 2-3 times as much water on Europa as there is on Earth. And it has global currents more powerful than Earth's as well. So how do we know this? And I don't have any idea if I have a slide that says how we know it. I don't. but that's okay. How do we know it? It was a happy discovery. The short, simple version is this. The Galileo mission to Jupiter carried a magnetometer. Now, a magnetometer on a spacecraft, certainly at the time, was kind of a nice to have instrument. It didn't take up much space, didn't take up much power. You put it on there and space physicists liked it. And you want to keep space physicists happy, I think, is a rule. It's the magnetometer that would discover what would go on to become probably one of the most remarkable discoveries in the history of solar system exploration. What it found specifically was a magnetic field emanating from Europa, right? Now, the thing is, Europa should not have had a magnetic field. Weirder yet, the magnetic field was pointed the wrong way relative to Jupiter. So this suggested, among other things, that maybe that magnetic field was being induced by Jupiter. So what does that mean? And how do we get an ocean from it? And that's a good question. The easiest way to think about this induced magnetic field is when you walk through a metal detector at an airport, right? When you walk through one, the metal detector is producing a high frequency magnetic wave. If there's a key in your pocket, the wave causes a current to flow through the key. And in turn, that generates a little magnetic field of its own. It's the induced magnetic field that triggers the metal detector. So it's not really detecting metal, it's detecting induced magnetic fields. Now, if we scale that to planetary scales, as Europa moves through Jupiter's magnetic field, a current courses through some sort of subsurface conductor, and that creates a miniature magnetic field flipped to oppose that of Jupiter. In effect, this subsurface conductor set off the Galileo metal detector. The hypothesis was not conclusive, though. It was possible that Europa had its own odd intrinsic magnetic field. It just happened to be oriented opposite Jupiter's. But the Galileo magnetometer team had a plan to test this. And I don't want to go too deep into the plan, but the simple version is Jupiter's big. It has a magnetic equator and a geographic equator, just like just like the Earth, right? Jupiter's magnetic equator is tilted by 10 degrees. So if you're Europa circling it, sometimes you're above that magnetic equator, sometimes you're below it. What the magnetometer team needed to do were take measurements when Europa was on the other side of the tilt from those first measurements. And if the moon's magnetic field changed directions, that would mean the field was induced by Jupiter, and therefore it possessed this internal conductor. The only thing that would fit the bill would be a subsurface saltwater ocean. And that had long been hypothesized, but it was just based on the physics, but it was very possible that the ocean had frozen over, hundreds of millions of years ago. But in January 2000, Galileo flew on the other side of the tilt. They found exactly what the models had predicted, and they had what would basically be solid evidence of a global ocean on Europa. So, about Europa. Who found it? This guy, Galileo Galilei. He found it in 1610. If you can see this picture, if you can see my screen, if you can see this picture of Galileo, you probably have seen this picture before. It is what I would say is probably the most famous photo of Galileo that exists. Notice a few things about it, if you would. He's old, right? He's balding. His hair is white. He has bags under his eyes. He's sort of slouching in his chair. He's holding his telescope. I mean, he looks wise, but mostly he just looks tired. This is not the guy who discovered the Galilean moons in 1610. When Galileo discovered, when he pointed his modified spyglass at Jupiter and discovered 3 and then 4 dots, and we have a picture of that right here, notes that he took. When he discovered these 3 or 4 dots sort of in the vicinity, in a line around Jupiter, this guy was preening, 46 years old, ladies' man, loved wine, women, and music, and he was famous. Galileo was, he's probably a great guy to invite to a party, but probably also the reason everybody leaves early. He was the smartest guy in every room he went in, and he let you know it. And back in 1610, you weren't going on YouTube or podcasts or incredible opportunities like George Mason University Observatory provides. What you're doing, you're going to salons throughout Italy and broader across Europe, and you're debating with other science, natural philosophers, right? Other scientists. You're debating the theories of the day, of your hypotheses. Galileo relished these debates. He always won, and he wasn't shy about letting everyone know that he had just won. And that's the guy who found Europa, not this guy we see on the screen right here. I think it's always important to remember that, because this was a pretty big deal, and it was just an absolutely impressive discovery. But also what's worth knowing, we all know how things ended for Galileo, right? So because we had objects circling another object in space, we had some evidence. This is sort of putting the Copernican theory of heliocentrism or hypothesis of heliocentrism to the test, and it's looking good. It's really a death knell for geocentrism in general. And when you coupled Galileo's observations with Kepler's laws, that would be the end of geocentrism evermore. Although I'm sure there are websites and Facebook groups devoted to it. I don't encourage anyone to go find them, because who knows what alleyways you'll end up in. Galileo, because of his discovery, we know ended up in house arrest for the rest of his life. Why? Because his discoveries contradicted scripture. That's sort of true. I mean, it did, but that's not really why he went to jail or why he was placed under house arrest. Because Galileo he just couldn't resist letting everyone know just how smart he was. And I admire this about him. He wrote a book, and unlike most scientists at the time, he didn't write it in Latin, he wrote it in Italian, because he wanted sort of the masses to be able to read it. And he put some pretty unkind words in the Pope's mouth. Basically, he made the church look stupid in print. And they'd been all along, they've been like, hey, just kind of go easy on us. And he's like, nah, I got to go for it. And he went for it, and they're like, well, now we're gonna have the last laugh on that one. So that's kind of I think that's an interesting thing to remember about, or to think about Galileo, that anyone that brash is probably worth remembering all these years later. So I guess that's a bit of a side note. What do we have here? We have some attempts to explore Europa. I'm going to walk briefly through a couple of these spacecraft here. These have been our attempts, or when I say our, I mean like the human civilization. I personally have no spacecraft, and I do not work for NASA, and nobody would want me to either design, build, or study spacecraft or planetary objects. So if you look at the top left, the first thing you're going to see is Europa Orbiter. The story behind this one is 1998, I believe. This was a proposal to NASA. So this was just before the hypothesis of a global saltwater ocean was proven. The thing probably cool to know about this is the idea was, we're going to send the spacecraft, it's going to orbit Europa. JPL, Jet Propulsion Laboratory, which is NASA's research and development facility in Pasadena, they thought they could do it for $400 million, and NASA headquarters was like, that's great. And they did the studies. They realized that the radiation shielding necessary was going to make this a little more expensive. So they went to NASA headquarters and they said, well, actually, it's $800 million. And NASA headquarters said, well, that's fine. This mission is canceled. And that was that. Next up, we see this incredible Star Destroyer looking thing. That's called GEMO. Technically, it'd be called Prometheus 1, but it was part of the GEMO project. GEMO stood for Jupiter Icy Moons Orbiter. This thing, and the reason the Millennium Falcon is next to it, it was about the length of the Millennium Falcon, right? This thing was enormous. The cool things worth mentioning about this spacecraft, which did not ultimately fly, as for reasons that will soon become clear. It is the size of the Millennium Falcon, weighs about as much as an 18-wheeler. It would require 3 launches to get its components in orbit, and then it would be assembled in orbit. So remember, this is like 2003-ish. And in 2003-ish, we were building the International Space Station. So NASA had cultivated a real skill set in and building things in orbit. And it would have been extraordinary. The other cool thing about it was going to carry a nuclear reactor. And the reason for all of this is the new NASA administrator at the time, his name was Sean O'Keefe. He was formerly the Secretary of the Navy. And as Secretary of the Navy, he saw this incredible submarine fleet, the nuclear submarine fleet, that could go anywhere, could stay underwater indefinitely, that just basically had infinite power. And he said, well, why doesn't NASA have the same thing? Now, it would have been extraordinary if this had happened. So he made the Prometheus project, it was called. And the idea was to build this reactor that could go into space, that could go on spacecraft. Eventually, it would go on human-rated spacecraft. So we would be using it to go to Mars. We'd be using it to go to the moon, and so on. The reactor is about the size of a trash can, right? So this wasn't an enormous thing. I think the main reason that GMO didn't fly is not because it wasn't cool, not because we don't need a nuclear reactor in space. We do, and that's something that I know NASA is working on right now, and I'm hoping to write a piece for Scientific American about that. There's your foreshadowing, I think, or your hint of what's to come. But the price tag. So remember, the first one, top left, Jupiter or Europa Orbiter, came in at 400. They said 400 million. It came in at 800 million, and NASA headquarters said, I don't think so. GMO came in at $10 billion, and this is in 2003 money. If you come in at $10 billion, you may as well come in at $10 trillion. You're not going to get that mission. And as soon as Sean O'Keefe left, Mike Griffin came in, first thing they did was kill GMO, just shot it dead. Next, bottom left, you see a Jupiter Europa Orbiter. This one was so close to flying. Enormous amounts of development work went into it. It was an extraordinary mission. It was going to it would enter orbit around Europa. It would do its prime mission in something like 30 to 90 days. It would collect everything you've ever wanted to know about Europa, the nature of its ice shell, the nature of the subsurface ocean, its composition, and so on. You'd map the ice shell in 3 dimensions, and so on and so forth. Unfortunately, I'm sad to say, the planetary science community decided we've got other priorities, and NASA agreed. The other priorities were Mars sample return. That mission is the Perseverance rover, which is now on Mars, which is why Jupiter Europa Orbiter is not flying today. Lastly, bottom right, we have the great Europa Clipper. That is the mission that will fly. I believe it launches in October or November 2024. I think it just passed its critical design review. This spacecraft, it has its wingspan, I think, is something like the width of a regulation basketball court. So it's pretty big. Those solar panels need to be, because it is not a nuclear powered spacecraft. It is solar powered at Jupiter. And that's something that we see with the Juno mission right now, which is doing extraordinary things at Jupiter. Europa Clipper is not going to orbit Europa. And that goes back to what we were talking about earlier about that Jovian radiation belt. It is, rather than pile on just the dumb radiation shielding, the metal that just absorbs that radiation so that those components inside don't get zapped and obliterated almost immediately. What they're doing instead is orbiting Jupiter. And as it's going to circle Jupiter, and every orbit it's going to encounter Europa. When it encounters Europa, it's going to scan a strip of it. And so it's zipping in and then it's zipping out. It's just flying right by Europa and getting away from it. That means it's dipping into the radiation and it's flying away. The only analogy I can really think of how that works in terms of radiation is like if you've got an ice cream cone inside, right? So you're sitting in your cool air-conditioned house, you've got this wonderful ice cream cone. If you go stand outside in the heat, in the hot sun, it's going to melt. But if you take your wonderful ice cream cone, you step outside for a minute, and then you step back in your house, it's not going to melt, or it's going to take a whole lot longer to do it. And Europa Clipper is working the same way. So if you look at a globe that would sit on your desk or in a classroom, you'll notice that the globe is basically made of petals that are sort of pasted onto a sphere. And that's not a perfect analogy, but it kind of works the same way with what Europa Clipper is going to do for Europa. It's going to get little strips, and eventually those strips can all be sort of pasted together, stitched together, and you get that 360-degree view, just as if you were in fact orbiting Europa. So it's a very elegant design. It's clever, and it's great for, there's my cat. It's great for ice shell science. ocean science. There's nothing this thing can't do. It's a bargain at any price. What do we have next? Another picture of Europa here. So I want to talk about one thing that's probably worth asking. Why do we want to have a Europa Clipper? Why do we want to go to Europa? Why is that a priority at all? It's a big solar system. Why don't we go to Titan? Why don't we go to a flagship of Pluto? Why Europa? And the answer is that global saltwater ocean. So let's talk a little bit about life, right? To create life as we know it, a world needs organic molecules, that's compounds with carbon, hydrogen, nitrogen, and oxygen, which most planets have, right? Life as we know it requires water for its processes, things like ingestion and metabolism and excretion. And while water, it's less common than organics, it's certainly found beyond Earth. Life lastly craves chemical energy, which is the toughest of the three to come by. Now, there's no sunlight in the ocean of Europa, right? Beneath that 15-kilometer ice shelf that you're looking at, it's ink black, right? And a consequence of that is there's no photosynthesis. But on the ocean floor, you've got water touching rock, which is conducive to interesting chemistry. And what Europa lacks in sunlight, it makes up for with sort of unbridled chemical reactions powered by something else. There are multiple hypotheses for what might be going on down there, but one of them that I certainly write about in my book, The Mission, which is available in bookstores everywhere. Though its seafloor is somewhat of a wondrous mystery, all the same, some have a pretty good hypothesis for what that floor looks like, right? It looks like Io. It's not quite as dramatic down there. I mean, if Io is Mordor, Europa has enough distance to sort of stave off Sauron's more malevolent designs. But those terrible forces causing Io to hemorrhage its entrails, right? The thing that's turning Io inside out, that's at work at Europa as well, but on its ocean floor. And these great geysers are gushing heat and chemical compounds from the mantle into that water. This happens on Earth too, but for different reasons. At the bottom of our ocean, we've got hydrothermal vents sort of ceaselessly billowing these columns of scorching water and providing an endless supply of nutrients from deep within the Earth. And life teems at these columns of water, right? Life simple and complex, and all in the total absence of sunlight. I want to mention Ganymede while we're talking about this. It's the third of those three moons, part of the orbital resonance, the 4, 2, and 1. Ganymede is the farthest of those three. Callisto's the last of the Galilean moons, but Ganymede is the third. It too is being squished by Jupiter, but because its ice shell is so thick, it only manages to melt in the middle. That means it's sandwiched between layers of ice. And its water is never afforded that chance to touch rock, right? Which is a bad thing if you want to get chemistry, and certainly the kind of chemistry that yields fish. Now, it's worth noting that nobody knows how you go from lifeless material to living material. It's the eternal mystery, right? Where did I come from? What scientists do know is that it takes a long time to happen. A celestial object can have all the right ingredients: organic material, water, chemical energy. But if the pie hasn't had time to set, so to speak, that world won't have life. The best guess for life's baking time in the oven, 500 million years. And Europa's ocean has very possibly had more than 4 billion years for life to get started. So if there's life anywhere beyond the planet Earth, it is Europa. And here's where we get to the sort of the philosophy part of Europa exploration. It's something that I'm going to end on because I happen to like it quite a bit. The sort of life that might be found at Europa is unlike the sort of life that we would find at somewhere, for example, Mars, right? That life is very likely not. Again, all of this is hypothetical, no matter what world we're talking about. But when we look at Europa, we're not looking for ancient microbes that went extinct 3 billion years ago, right? We're looking at conceivably certain possibly life, conceivably complex life that's extant today, that's had a very long time to evolve, that very likely has not gone through multiple extinction level events as we've seen on Earth. And whatever life we find there would be life as we know it, but it would be life unrelated to what we find on Earth or conceivably on Mars. So there have been some pretty interesting papers come out last year and actually over the last few years. One I found very provocative. If there's life on Mars, there's a good chance that life came from Earth, right? Because we've gone through these multiple terrible cataclysmic impacts that have kicked up all sorts of Earth into space. I read an interesting piece not long ago that said, because the Chicxulub crater asteroid, for example, was so powerful, there's a very good chance that if we dig enough on the moon, we would find dinosaur bones up there. I mean, that would have been thrown up there. If life was on some of this stuff and it made its way to Mars, we could have very easily sort of pollinated Mars. A very, I find, provocative hypothesis is that life on Earth came from Mars, like the exact reverse happened. And these aren't like, these aren't crackpot theories or Oumuamua type alien things. I mean, these are legitimate papers and serious scientific journals. But that's not the case on Europa. Whatever we find on Europa would almost certainly be entirely unrelated to what we have on Earth. It would have experienced its own genesis, right? It would have had, as I have in the subtitle of my book, which I will kindly read you, it would have had its own Garden of Eden at the bottom of an alien ocean. What would such life look like? And here's what I mentioned, could we eat that fish? So here's the cool thing, and this is what I'm going to end with, this thought. To the extent that it is morally justifiable for anyone to eat meat, the justification is this. This fish on my plate at a restaurant is mine to eat because my ancestors over the last 100,000 years established my place in the food chain. And my place in the food chain says, this I can eat. I am morally allowed to do it simply because of the laws of nature, if you would. Interestingly, let's say there are fish swimming in the European Ocean. Those fish are not in our food chain. We have earned no right to eat them. Our ancestors did nothing on Europa. Would we even consider such a fish to be an animal? Again, it's wholly unrelated to us. What is a non-Earth creature in relation to life on Earth? These are questions that science fiction is really good at asking, but what's really cool is that these are questions that in our lifetime, we might actually have to answer. So that's why we want to go there, to truly, to do something truly new, to dare mighty things, as JPL's motto is. So I will end the talk there. There's a picture of my book, if you can see it. You can find more about me at davidwbrown.com. I'm on social media at DWBWriter. That's Instagram, and unfortunately, that's also Twitter. This is my book, which I have right behind me, right there. It's beautiful, feels great. Mother's Day is coming up, and I can't think of a better way to tell Mom I love you than the gift of The Mission, or how a disciple of Carl Sagan, an ex-motocross racer, a Texas Tea Party congressman, the world's worst typewriter saleswoman, California mountain people, and an anonymous NASA functionary went to war with Mars, survived an insurgency at Saturn, traded blows with Washington, and stole a ride on an Alabama moon rocket to send a space robot to Jupiter in search of the second Garden of Eden at the bottom of an alien ocean inside of an ice world called Europa. A true story. So thank you very much for all your time. Thank you for joining me tonight. And if we have any time for questions, I'm happy to take them. And I'm going to figure out how to end my screen sharing now. Let's see, stop share. There we go. Okay, that's all I know what to do.
I think we can take it from there. Thank you very much. That was an excellent talk. If people want to show their appreciation in the chat, I'm sure that will be appreciated. So yeah, now we'll have our Q&A, and afterward we'll do our tour, which David, if you want to hang out for and see what we have to offer, you're more than welcome. And possibly if more people have questions in the chat, then we can field those as well. So I am going to take the host sort of prerogative and ask you the first question, which is, what made you interested in Europa to begin with?
As a so as a storyteller, you're always on the lookout for some sort of tale that has high stakes, compelling characters, and just an interesting story in general. And the stakes are the thing that first caught me. I mean, what could be more important than the discovery of life on another world? That has implications for philosophy, for religion, for, of course, for science and biology. It would be like nothing ever discovered before. So right away I was hooked, and the idea of actually going to find this out. Now, Europa Clipper is not a life detection mission. It's something I wanted to mention earlier. It's a habitability mission. So it's going to figure out the nature of habitability on Europa and where best to find it. A lander, a subsequent lander, is going to go there and sort of, scratch around on the surface, kind of saw its way in and do analysis of what it finds. Then I met the people behind it, and they were so incredibly engaging. They had been in the trenches for so long. I mean, some of these scientists have been doing this for 20 years, trying to get this mission going. This mission had been approved and canceled more times than you can count, although it is in my book, which I encourage you to buy. They'd been in the trenches for so long. When I started talking to most of them, it felt almost like therapy. I don't think many of them had really taken the time to just stop and think about what they had achieved and how hard it had been. And the more I got their stories, the more I fell in love with them and sort of their tenacity and their quirkiness and their senses of humor. And of course, the story itself is just an incredibly engaging one. I mean, no one goes into planetary science, certainly not if you're studying the outer planets, if you need immediate gratification. I mean, these missions take decades to get going, and sometimes a decade to actually get to its target. You're looking at an entire career just to get the opportunity to answer the question and not even answer it. So, what kind of people do that? And I just fell in love with that. So the whole thing, it was like a holistic falling in love, I guess you could say.
Excellent. Yeah, I have tremendous respect for folks like, for example, with New Horizons with the Pluto mission, because these are folks who spent their entire life essentially for this one mission, for just that relatively quick flyby, to see what was going on with the world. That's interesting that you that's what the characters are what brought you to this story. And I could tell that you definitely like the characters in history with your enthusiasm for Galileo. That entire revolution, the heliocentric revolution, was one of my favorite eras in astronomical history. And my tidbit I will say with Galileo is that Kepler actually sent Galileo his laws, and Galileo essentially just blew him off. I don't even think he returned the letter. He just completely ignored Kepler. Yeah, Galileo was quite the character. All right, so let's get some questions from the chat. I believe the first one was from Randy Warren, and it's a fairly straightforward question. Does Europa have a liquid or solid core?
I know it's iron. You would probably need to talk to a planetary scientist and/or Wikipedia about that one, but I don't have the answer for you, I'm afraid. So any questions like what is the composition of the surface, I'm probably the wrong person to ask, but I'm happy to, I certainly talk about programmatic and mission stuff.
Yes, it is definitely a rocky iron core. I can attest to that. Let's see. Nuclear material in space, what could possibly go wrong?
It's not like there's radiation up there.
Azan asks, does the intense radiation mean life cannot exist on Europa? or in Europe?
No, presumably not. I mean, we don't even know, we don't know if life exists there at all. To get beneath the irradiated surface of Europa, you have to go down about 10 centimeters. And that's what the Europa Lander would do. Once you get below 10 centimeters, you're in sort of more pristine Europa. I would imagine that the ocean is relatively safe. It seemed interestingly, that ice shell, because of that radiation, is an enabler for life, right? So these ions are endlessly bombarding the ice shell, basically oxidizing is not the right word, I don't think, but because of the plate tectonics of Europa, these plates are being pushed beneath each other in the surface. And in an elegant plate tectonic system, it's the first non-Earth world to have had plate tectonics discovered on it. This is what oxidizes the ocean, and this is what actually makes it more conducive for life as that ice gets pushed into there. So I'm going to say no. In fact, I'm going to say it's an enabler.
Yeah, water and ice actually are an effective radiation shield. So I would suspect that I would agree with that assessment as well. Margaret Rigel, and I apologize if I butcher anyone's name. She says, thank you. She's definitely getting the book. Let's see.
Excellent. Everyone should be saying that.
A lot of thank yous.
Thank you very much, by the way.
There was a much appreciated the simple analogies you made to turn complex concepts into more digestible ones. Next question comes from Mallory DeBar. She asks, how long would it take for a clipper to get to Europa?
If I am not mistaken, it's going to take 6 years to get there. So it launches in 2024, at the end of 2024. We're looking at 2030 by the time it gets there. Originally, Europa Clipper was going to launch on the SLS rocket, in which case it would have taken it would be just a direct shot straight from Earth to Jupiter. And it would have gotten there in like 2 or 3 years. And that would have been the optimal solution. Unfortunately, SLS ran behind schedule and is repurposed now for the Artemis program, which is NASA's plan to put astronauts back on the moon and presumably Mars afterward. So studies have been conducted. What other heavy lift rocket can we use to get to Europa? And there aren't many. In fact, I can think there's only one that can basically do it, and that's the Falcon Heavy. It would launch. It's going to use what's called a mega trajectory. So it's going to launch from Earth. It's going to go to Mars. That's the M in mega. It's going to come back to Earth, and it's going to get a gravity assist and get flung basically to Jupiter in sort of what they call a slingshot maneuver or a gravity assist. And so, yeah, 6 years from launch to get there.
Oh, no problem. That's a grad student's thesis. I like to think of things in terms of thesis lengths. Mustafa Al-Falahi, again, I apologize. I am crap with names. They ask, is the liquid found on Europa warmer than our ocean?
I don't know the answer to that. I don't know who would know the answer to that. I'm sure physicists have probably worked that out to a great extent. I'm going to say that because of the extreme pressures involved, certainly because of that ice shell, you could have liquid salt water at different temperatures than you get it on Earth. It's going to be cold. I mean, it's relatively warm, but we're using the word relative here for extreme values of relative. So I'm going to say I don't know.
I also have to admit, I don't know either. Planetary science is not exactly my forte, but I would imagine that it also depends on what level you're talking about. Because as you mentioned, near essentially the ocean floor, it's going to be far warmer than near the top of the ice sheet. So I'm not entirely certain how warm it gets there, particularly in regards to, say, thermal vents here on Earth. Andrew Wilson asks, so is there no sign of water on any of the other moons?
There is, oh, well, of course, you've got Enceladus, which has its own subsurface ocean, and it's blasting it into space. I mean, that's the obvious answer. It's possible that Titan has a subsurface ocean as well, in addition to its stable liquid hydrocarbon lakes on the surface. We find ice everywhere. I think there's ice on Ceres. Well, of course, there's ice on the moon. There's ice on, I think, Mercury. Probably no water on Venus, though. So yes, the answer is liquid water. Absolutely, we must go to Enceladus after we get a Europa Lander to scratch into that ice.
Yeah, Enceladus is fascinating in that I think it was a couple of years ago now. I want to say Huygens went through one of actually serendipitously actually went through one of these basically cryovolcanic eruptions and discovered of the 6 elements that are necessary for life, 5 of them were located in that outburst. So certainly is. It's certainly a sort of a positive sign, as it were, that Enceladus, like Europa, could very well be host to some form of life, as it were. Let's see. Randy Warren asks if you indicated that we would expect to have life, if possible, would have had, butchering this question. You indicated that we would expect to have life, if possible, would have been generated by the interaction of the core elements with salty ocean. Do I understand that correctly? And also, can you talk a little bit more about the radiation belt, Jupiter's radiation belt?
I'm sorry, what was the last part?
Jupiter's radiation belt.
Oh, well, I'll answer that part first. So where does this radiation belt come from? And forgive me, physicists, for oversimplifying to the point of gibberish, but the interior of Jupiter has pressure so massive that you get what is called, or you get basically a liquid metallic hydrogen core. Because this liquid metallic hydrogen core behaves essentially like a lava lamp, right? So at the very center, it's super hot. As it rises, it cools, and then it comes back down, and it's just constantly doing this. And this is one of the things that's generating that incredible magnetic field. As particles fly through space, they get caught in it, they get accelerated in the magnetic field, and ultimately you get this massive, grotesquely inhospitable place in our solar system. Probably that would be like the biker bar of the solar system, right? This is not the place where you want to hang out. Whenever I see movies that take place on the surface of Europa, I mean, if the movie lasts more than an hour, I think it would probably be unrealistic because they would be dead of cancer by then. So that's kind of the nature of the beast. The first question is to the best I understand, I would say that, I mean, obviously, salt water would be essential in this case, though you may want to talk to an astrobiologist if you want to go into sort of the real hardened details of how that salt water is going to interact with the various elements in order to give us that life that we want so desperately.
Excellent. Our TA William asks, out of all the missions currently in development now, which one would you like to see the results of most and why?
Out of all the missions in development or actually going to fly? So in development, I would certainly like to see Europa Lander fly for obvious reasons. Because I've invested, I mean, it took 7 years to write this book, so I feel fairly invested in the story. I'd like to know the answer to the life question in my lifetime. The mission that I'm most excited about that is another mission that I would love to see fly, and that's in development, and that's in the final stages of the Discovery selection, which is NASA's small mission class, is the Trident mission, which is flying to Triton, which is an ocean moon of Neptune. Again, this is a world that quite possibly is habitable. And what's cool about that is Yeah, for most of my life, I mean, for most of my life, because I feel super old right now, the habitable zone of the solar system was like Venus, Earth, and Mars. And then because of the ocean of Europa, suddenly it's Venus, Earth, Mars, Jupiter. And then we start talking about Titan, and we start talking about Enceladus, and then we add the habitable zone of the solar system to, we add Saturn to it. And now it's looking like we're going to go we're going to have the entirety of the solar system being the habitable zone. I mean, I saw a paper a couple of years ago positing, how life would work on Mercury. So the habitable zone of the solar system is the solar system, it would seem. If Pluto, for example, has a subsurface ocean, I mean, the sky's the limit. Um, so, so yes, getting to the ice giants is critical, and the Trident mission can do it relatively fast. The coolest mission that's about to fly, aside from Europa Clipper, of course, which is my favorite, is going to be Dragonfly, which is a quadcopter that is being built by the Applied Physics Laboratory in Laurel, Maryland. And this quadcopter is going to, it's going to land on Titan, which again has its stable seas on its surface. It's not necessarily going to land right next to the seas on the outset, but it's basically like one of those drones you can buy at online. It's got the 4 blades. It's a little bigger than that. I forget the dimensions of it, but this thing is going to take off, fly, have its camera on. We're going to be flying around in this other world the same way that a drone flies on Earth, because Titan is the only moon in the solar system with a significant atmosphere. It's going to land, it's going to do in situ science, and then they're going to plan the next place. So they're going to fly back in the air, they're going to look around, and they're going to say, where are we going to go next? How extraordinary, right? I mean, the nature of exploration of the solar system is now requiring air travel. We're doing it on Mars this weekend, I think. Yeah, with the Ingenuity helicopter, and if not, that didn't fly today, did it?
I don't believe so.
Okay,
I think they postponed it to the weekend.
Okay, so we're gonna see flight on Mars, and I don't think after this thing flies, I think it's gonna be such a public relations bonanza that I don't think we're ever going to send an object to Mars, to the surface of Mars again without some sort of aerial element. We're going to be flying the skies of Titan soon, so who knows? I guess Venus is next. We'll get our cloud cities after all.
That would be very interesting, since the Soviets are the only people who have actually managed to land anything on the Venusian surface that lasted more than an hour.
Yeah, Cloud City actually was built in like the clouds of the gas planet. So that wouldn't apply to Venus, but close enough.
All right, I think we're going to transition at this point to our closed dome tour. David, if you want to hang out, I can ask you a few more questions while William is transitioning from one object to another.
Sure.
Okay, thank you. All right, William, you can take it away. Or I should probably ask, are you ready for us?
Yes, I'm ready. Okay, so let me go ahead and share my screen. So let's get this going. Okay, and minimize some stuff. All right, wonderful. So what you're looking at is the desktop of one of the computers that we have on campus. So earlier, Dr. Parks showed you a view of our observatory. It was on the opposite end of what you see here. So the wallpaper for this desktop is, of course, our observatory. So the control room is this little building right here. So we're connected to a computer that is inside there. So this is very, very convenient and wonderful. So we can keep tours going during all this quarantining and pandemic stuff. And we can also do our research observing from the comforts of our own bed. The downside is that it's a little bit easier to fall asleep when you shouldn't, but everything's got trade-offs. So one of the things that makes it possible to observe remotely is that we have a series of webcams installed around the roof. So if I pull those up, you can see some real-time views of our observatory. So in the top right, We have the control room. So we are currently connected to this computer right here towards the middle left. And then in the bottom left, we have a secondary computer that's in theory a clone of the first computer where we do all of our software testing. So this is a nice little cozy room where research observers will usually spend their nights, or will spend their nights if they're observing in person. And that's pretty much all there is to that. In the bottom left, you can see we have an outside view of the observatory, and the rain is coming down, so definitely don't want to open the shutter now. But you can still see that the housing for the telescope is fairly large. Here is a door frame for scale. It's about 6.5 feet tall. And yeah, that's pretty much what you're going to get out of this view. And then lastly, we have a view inside of the dome at the actual telescope. And so Patrick can talk to us a little bit about this telescope we have.
Yep. This is a 32-inch or 0.8 meter in diameter Ritchie Cassegrain telescope. That's just describing the way the mirrors are curved and where they're located. Will is working with the software to point the telescope so we can look down the barrel and see what the insides of it are like. And so here you can see it turning on a fork mount. This is one of the motors for pointing the telescope. And if we could go here in person, be pointing out the feature of this. It's got a plexiglass cover specifically so you can see the motor in operation. The dome will track with the telescope ultimately unless we don't have it synced at the moment, but normally it will for observing purposes because otherwise that small slit opening would not be particularly useful. It was not connected earlier. Oh well. Closed dome, it doesn't matter too much. Yeah, so now you can start to see that telescope is actually mostly empty space. That there's a large curved mirror at the back of the telescope, and this smaller mirror at the front. So when it's pointed at an object, light enters the front of the telescope, goes all the way down to the. Okay, yeah, we can see most of the telescope already. Light enters the front of the telescope, goes all the way down to the back of the telescope, bounces off this primary mirror that's the 32-inch in diameter, where it's focused up to the secondary mirror, which is, I want to say, about 12 inches in diameter, still decently large, and then goes back down through this hole in the primary mirror and into beam splitter, and we can shunt it off to the various pieces of equipment we have hanging off the back of the telescope, eyepieces, cameras, a low resolution spectrograph, that sort of thing.
Pretty cool. So Patrick, how expensive is this telescope? Is this $1 million worth of equipment we're looking at, or?
I've seen conflicting figures. I want to say it was a few $100,000 in total. And so that, and the higher numbers probably like on the order of 800,000, including the whole construction cost for the dome. It's like the telescope had to be brought up here on a crane and then the dome assembled around it.
Right, yeah. So the telescope itself is around $300,000. So it's actually a lot cheaper than what most people would usually think. The dome itself is around 80,000, and that's most of the cost there, although between 2018 and 2019-ish, we did put in some upgrades to the telescope, which totaled about $150,000. So those upgrades were mainly to improve the pointing of the telescope, which just means that when we tell it to go to a target, it will actually go there and lock onto it, and we won't have to do any fine adjustments. Okay, so Patrick, is there anything else you want to say about the telescope?
I I don't think so, unless I forgot something obvious about it.
No. Okay. So if there are any questions about the telescope or anything else about our observatory, you can feel free to put them into the chat. But for now, we can go ahead and move to showing you a few canned images that we've taken beforehand with this telescope. But before we do that, if there are any questions in the chat for David that we want to address, now would probably be a good time to do that.
Yes. So, David, if you're still with us.
I am here.
Excellent. Peter Lackinen says, apologies if this is addressed. I missed a part when dinner was delivered. Will this Europa mission explore the ocean? I remember speculation of submersibles heating up to sink through the ice to reach the ocean below. Anything like that as part of this first mission?
Not Europa Clipper and not Europa Lander. So in terms of missions to Europa, the only, so various missions have flown by. For example, the Voyager missions are the ones that first captured the world's attention that this creepy looking place like Europa even exists. And various spacecraft have had flybys of the Jovian system and have caught glimpses of Europa. The first up close and personal looks that planetary scientists ever received was from the Galileo mission. The Juno mission at Jupiter right now is in its extended mission is going to become a planetary system mission. So it's going to be getting looks at different moons, different moons of the Jovian system. So I don't know if it's going to, if Europa is part of that in this extended phase or not, but I would imagine at some point Europa will be. In terms of getting pictures of the ice, getting into the ice, and getting beneath the ice, these are obviously the long-term plans. So Europa Clipper is going to, like I said, it's going to characterize the habitability of Europa. It's going to actually get pictures of the surface. So one of the neat things is when we look at pictures of Europa, it's like looking at a picture of the Earth from say the Apollo program, right? And then you say, oh, and by the way, I'm going to land a helicopter in Central Park using just a picture of the Earth from the Apollo program. It's just not possible. To get a Europa lander onto the surface of Europa, it would be greatly aided by imagery of the surface. So there's really no imagery of what that surface looks like. So the Europa lander people believe that they don't actually need that imagery, actually using Perseverance lander technology in order to do it. And I tend to trust the judgment of the lander people. So I'm going to say that, yeah, we can go ahead and let's fly that thing. So the lander is going to be the thing that saws into the ice. It's going to get about, like I said, about 10 centimeters down, and it's going to look for evidence of things that once wiggled. The next step, the hard step, or a next step, not necessarily the next step, is to get into that ocean. How do you do that? Melt probes have been the thing historically discussed. Right now, melt probes are still science fiction. I don't see that happening in our lifetime unless NASA gets a huge budget, and particularly if life is discovered on Europa. If we get evidence of life, then yes, in fact, I think that something like a melt probe or some sort of way to get into that ice would become a priority. But we have to remember that NASA gets 1/2% of the federal budget. It's working from change from the couch cushions, right? It's a rounding error in the Pentagon budget, or relative to the Pentagon budget. No money means no exciting missions to find fish on other celestial objects. So let us all write our Congress people and let them know, yea, verily, we would like to do better. So fingers crossed that happens. But in the meantime, no melt probes in the foreseeable future, but getting into the ocean is essential. And that is part of the long-term sort of notional strategy.
Cool. I'm going to take, again, my prerogative and ask you another question before I let William proceed. And that is, given the shall we say, the Oumuamua controversy, there is becoming a renewed discussion as to what place talking about alien life is appropriate within the scientific community. So I was wondering, with the people that you encountered with during when you wrote this book, how much of that was on their minds when they were looking at Europa, moving, what are their goals towards Europa? Is finding life on the forefront of their mind, or are they just simply more scientifically motivated?
That's a great question, and there are multiple dimensions to that answer. I will try to address that one concisely. So if we just talk about regular geologists, like cold, dispassionate geologists, as they tend to be, they're interested in that weird looking ice shell. What's going on there? How does Europa work? How does its plate tectonics work? What do the chaos regions look like, and the scalloped terrain, and so on and so forth? What do all these things mean? And how do you get a world like this? What is its history? Ultimately, though, everybody knows that the thing that's writing Europa's check is the life question. And everyone on the team that I've spoken with certainly talks about the life question. They want to know, because it is a habitable world. And if it is a habitable world, let's see if it is in fact inhabited. You would be very hard pressed to get, project scientists or deputy project scientists to say, we're going to find fish, but simply because, nobody wants to really go out on that ledge, because again, like you said, it's kind of a bold claim to make. Now, I will say this: the person who actually, in fact, got money for this mission, which was John Culberson, a congressman from Houston, or a former congressman from Houston. I dare say, I assert unambiguously that without Culberson's enthusiastic support for Europa exploration, Europa Clipper would not have been funded. Europa Lander certainly wouldn't have gotten the hundreds of millions of dollars that it got. Culberson believed, he was in fact certain, that life is in that ocean. That was the only thing that mattered to him. And his belief was, if we find life on another world, which he believes this is the world to find it, then it would galvanize the public in a way unlike seen since the Apollo program, since astronauts walked on the moon. And NASA would finally get the sorts of budgets that it needs to do this robust exploration that we talked about, to get the money for things like melt probes. So to the extent that the life question is urgent, it is exceeding, it has been the driving force behind getting this thing going. Is it the most important question for many of the scientists? Well, that depends. I would say, for example, if you're characterizing the ice shell in 3 dimensions, what you're looking at is the ice-ocean interface. And why does that matter? Because that's very likely where you're going to find evidence of life, or in fact, life itself. If you look underneath Antarctica, like the ice shells of Antarctica, it looks like brown sludge down there, and fish like to feed on it. Penguins go down there, and it has all its little, various microbial life. So there might be something very similar at the bottom of Europa's ice shell. And so it's a pretty good idea to know what that looks like. So some yes, some no. Now, I've seen nobody be so irresponsible as we've seen with the Oumuamua stuff, if I may be so bold. But, if the Europa camera captures some sort of sea life lumbering along the Europa surface, then I think people might be a little more cavalier.
Yeah, I have to admit that I have an interest in, obviously I have an active interest in SETI and searching for extraterrestrial intelligence, but what I'll admit to is I am not so much interested in what that life looks like as to what our life will look like once we find that out. As you pointed out, the implications of life beyond our planet, particularly intelligent life beyond our planet, would affect essentially every aspect of our existence. But that's
I would like to see what life looks like on Titan, in fact, because that would be life as we don't know it. That would be an entirely different, that would be an entirely different foundation for life. So And I've seen papers. I think Jonathan Lunine was a co-author on one of them, but I can't remember the first author. And that paper was enormously compelling, like with how that life could form. So I don't know. I'd love to see it. Give me anything. I'll take anything on another world, microbe, whatever. I would prefer the aliens with the big eyes and the little gray bodies, but I'll take anything.
I would like to see something at least multicellular, simply because there is obviously the conversation or the discussion of whether or not we've already contaminated Mars, for example,
Right.
with bacterial life. So that would be, I think, if you find multicellular or evolved life, then I think that is just definitive proof, as opposed to, oh, we just contaminated it somehow with our instruments. So but yeah,
that was one of the motivating. That was I know that we're moving on, but that was one of the motivating factors behind the Outer Planets Assessment Group, which formed right around the time that Europa exploration really started moving along. We've got this ocean on Europa. At the time, the Mars program's driving mantra was follow the water, right? Because there was evidence that possibly water once flowed on Mars, and if water once flowed on Mars, there might have been life. So follow the water, right? Well, the Outer Planets community said, well, we want water. I got a place for you. Forget follow the water. We want to follow the whales. So yeah, I would like to see that multicellular life myself. I don't know that I'll get super jazzed by an amoeba on Mars, but I'll take what I can get. I do wish Perseverance had gone. One of the options for its landing site was going to be, I think it was one of the previous rovers, and it was going to look to see had microbial life survived on this rover, like what's on this thing. I think Jezero Crater ultimately was probably the better choice, but that would have been cool to roll around a rover that's already on the planet Mars.
Maybe that'll be the next helicopter mission on Mars.
There you
So-
go.
All right. Well, I don't want to keep William waiting, so I'll hand it back to you, because I can have this discussion with you for hours, to be honest with you.
Yeah,
So
and I'll be happy to.
excellent. So William, back to you.
Okay, wonderful. Thank you. So in the spirit of Jupiter and, its fairly near neighbor Saturn, we can show a picture that we took of a very spectacular event not very long ago. So let me pull this up and we can zoom in on that. So what we're looking at happened on December 21st, 2020. So you might remember this event being called the Great Conjunction, and we held a live viewing event for that. And what happened here was Jupiter and Saturn appeared to be very, very close on the sky. It's important to keep in mind, though, that they're not close in physical space. There's still a third dimension here, the depth that you're not really seeing. So Jupiter and Saturn are still very far apart, but the point is, on this 2D surface of the sky, they look like they are very, very close. Now, conjunctions like this aren't all that rare, but what is rare is how close this one got. The last time the Jupiter and Saturn were this close in the night sky was about 800 years ago. So it's been a very, very long time since we've had a view like this. And what you can see here are, of course, Jupiter and then Saturn down here. So what's nice about closed dome tours is that we can show you images that we have processed and cleaned up a little bit. Usually when we take images, or all the time when we take images with our camera, they will immediately come out as black and white and kind of grainy. So that's just, a fact of raw images. So when we show you these canned images, usually they are a bit more cleaned up and processed, and they look a little bit nicer than what you would get with a raw image that we took, that night. So you can see that we have Jupiter, and you can make out a little bit of the banded structure on Jupiter, and then you also have some of Jupiter's moons out here. I can't tell you which one is which, unfortunately, though. I'm not quite sure of the orientation there. And then in the, of course, we have Saturn. It's a little bit more redder than it normally would appear. It's just an artifact of how we colored the image. So you can color images in a bunch of different ways. But you can still see Saturn's ring structure, quite nice. So one thing to note, or one last thing really to note about this image, is that it may not be as detailed as you were expecting. So if you Google, Jupiter or Saturn on Google Images, you get these wonderful, exotic HD photos, and that's obviously not what you see here. So those photos that you see on Google Images were taken by, something like the Hubble spacecraft or by probes that have flown by those bodies. And it really just highlights the need to actually put telescopes in space so we can get crisper views, so we're not limited by the atmosphere, and also sending missions directly to these objects so we can get better data, better images, and so forth. So with that, I can hand it over to Patrick to talk about the second image of the night.
Okay, so this is going to be an image that should... Wrong button, one moment.
Yeah, I saw you disconnect from the NC viewer. I was like, oh no. Okay. And you're back, cool.
Yeah, sorry about that. I mean, there's two close buttons right next to each other, so it's easy to do.
Yeah, that's my biggest fear. Thankfully, it hasn't happened to me yet.
Well, that should get it over with. That in this case, looking at object of much larger angular size, so that it actually fills up the field of view. Although it looked like it wasn't quite the best conditions tonight it was taken, since things are a little bit blurry. But this is an example of sort of black and white image that Will was talking about. And if it looks vaguely familiar, like there's an eagle here, that's because it is the Eagle Nebula, or M16. This is an emission nebula backed up by an open cluster of stars that recently formed in it. And it's in the constellation Serpens, vaguely in the direction of the galactic center, about 5,700 light years away from us, or like on the order of a quarter of the way to the galactic center. But it's a pretty rough direction there. I wouldn't recommend that if you're trying to use it as a landmark. And this particular image is very much not in true colors. That if we colorize this with the filter is taken in, it would appear to be roughly cherry red. It was taken in H alpha or hydrogen alpha. That's this emission line generated by the element hydrogen, which it does a lot of when the gas is excited by, say, a lot of ultraviolet radiation coming off of a number of hot, bright stars like are here. This is a pretty typical star forming region. Probably seen the infamous Pillars of Creation image taken by Hubble in '95, which used different wavelengths than we have here and focused on this pillar region in particular. There's a lot of ongoing star formation, which is ultimately going to blow away all of the gas, but that's, I want to say, in the order of a few million years in the future. And
so there's a question in the chat to confirm, is this the Eagle Nebula that we're...
Yes, this is the Eagle Nebula.
And Randy Warren has been talking, or has been asking questions about the colors specifically. And you, William, you may have addressed this when you were talking about Jupiter, but the colors that we saw on Jupiter, are those real? Are those true colors, as in, are those the colors that we would see from the reflected sunlight from those worlds? And kind of following up on this image, what would be the true color of this particular galaxy or this particular nebula?
Okay, yeah, so a lot to that question. I'll let Patrick answer the part about what color the Eagle Nebula would actually look like. But if we go back to the conjunction image that I unfortunately think I closed. That is unfortunate. I can fish that up right quick. I can take a look at all of our images that we have saved here. Okay. So it's a little hard to make out the coloring of Jupiter. So you can see that you do have this brighter kind of reddish brown hue going across the middle of Jupiter. And it's actually fairly realistic to what you would actually see. So Jupiter itself has a banded structure. It has alternating, compositions and winds grinding against each other in these different belts. And some of the belts are a lighter white color, and then some of the belts are a redder brownish color. And so the coloring in this image for Jupiter, it's not perfect, but it's also, I wouldn't say it's that far off. You see, something here that's like a red blob and some other weird artifacts. That's of course, not real, but for Jupiter's surface, I would say that this is, it's okay.
Okay, for the Eagle Nebula, it's sort of complicated. That I mentioned. Well, I mentioned that this was in filter in H alpha, which is roughly red. I think 656 nanometers approximately.
Yeah, correct.
Yeah, that if you're looking at this through the eyepiece of the telescope, it would actually appear gray like this because it's not actually all that bright. There's only so much we can do to make it brighter with the telescope. So you'd still pretty much be using your night vision for it, and that's why it would appear gray. Sometimes bright nebulas can appear vaguely greenish because your eyes are relatively sensitive in that region. And well, not this one, some emit a lot of light in that wavelength range. This one put out a moderate amount, but that's getting into the weeds about emission spectra.
Excellent.
Okay, cool. Are there any other questions in chat we could answer, or should we just go on to the last object?
Well, there's one question from Andrew. Asks, can or have planets overlapped when we've looked at them? So can you have an absolute conjunction?
An absolute overlap? Is that the question?
Mhm.
I suppose, in theory, it's possible, but it's very, 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 very unlikely. So I don't think we've ever seen something like that happen, but as far as I know, I don't think there's grounds for it being theoretically impossible.
Interesting. Yeah, I would concur with that. I think that it's just, pun intended, astronomically rare for that alignment to happen. Because we're talking about objects that are exceedingly small on the sky, and well, space is huge, so it is possible, but it would be very, very uncommon.
Right. Okay.
Mhm.
So then let's go ahead and talk about the, oh, there's a raised hand. Okay. From Ibrahim.
Okay, so what was the first thing we saw?
Oh, the first thing we saw was the December 2020 Jupiter-Saturn conjunction.
I remember hearing about that. I didn't see it though because I was busy that day.
Yeah.
So
Okay.
was that in the Eagle Nebula?
So yeah, this one and the Eagle Nebula. And then we'll show one more object. Okay. So let's go ahead and move on to the last object. So this is one you all will certainly be familiar with. I'm sure you've seen it before. So if we open this up, what we have is a very nice picture of the moon. So let's see if I can do a little. Yeah, playing with the zoom on this is always a pain. Okay, that's a little better. So, all right. And here we have our closest astronomical friend, the moon. So as you might know, this sky was formed about 4.5 billion years ago. The leading, theory behind how this formed is that when Earth was still molten and cooling from its formation, there was about a Mars-sized object that collided with the Earth. It kicked up a bunch of debris. That debris orbited the Earth and eventually coalesced into the moon. So this, the moon is around 250,000 miles from Earth. It's about 1/100th of the mass of Earth and about a quarter of Earth's diameter. And what's neat about the moon is that it is in what we call a synchronous rotation with the Earth. So what that means is the same side of the moon is always facing us. So at any given time, we are only seeing part of the moon. So it's colloquially called the near side of the moon, as opposed to the far side of the moon or the other side of the moon. So some of the features you immediately notice when you look at the moon is you have these darker indents on the moon, then you have these lighter patches. So the darker areas are called the lunar maria, and the lighter areas are called the lunar highlands. So the maria were carved out by old volcanic eruptions and lava flows. And what's neat is that these maria are virtually absent from the far side of the moon. You won't see a whole lot of these on the other end of the moon. So another thing that you notice is that you have a lot of impact craters. So if we zoom in quite a bit, you can see among other imperfections in the image, you have these very small kind of circles with holes in them that are very regular, very sharply defined. So that is actually just a problem with our camera that we are currently troubleshooting, and that's not in any way related to what's actually on the moon. But what is on the moon are these craters, all of these impact craters that are just completely littering the surface of the moon. And one of the things that keeps craters on the moon for so long is that the moon doesn't really have any weathering process. There's no erosion on the moon. So when something smacks the surface of the moon, it's going to leave a mark, and that mark is going to stay there for a while. There's no wind to erode it away. There's no water to erode it away. There's nothing like that. So it's going to just hang out for a while. So when we're looking at the surface of the moon, we're basically looking at an impact history of the moon over the course of its life, which is pretty neat. So that is pretty much everything I wanted to say about the moon tonight. And I think unless there are any additional questions for David or me or Patrick, then I think we can call it a night.
We do have a couple of questions, one of them from Andrew Wilson
Okay.
about the moon. And I would like to ask if David is willing and is still around. I have one final question from the chat for him as well. So Andrew Wilson says, have we never sent anything to the other side of the moon to map it out? And have we really never seen anything on the other side?
Okay, so we have seen the other side of the moon, the far side of the moon. I believe it was the Russians who sent a probe to the far side of the moon. And that was, late 1900s, I believe. I forget exactly when. But we have taken images of the far side of the moon. And like I said, it's got less maria. And I believe it also has fewer impact craters than the near side of the moon, which is kind of contrary to what you might expect. So we have taken images of the far side of the moon. We have sent probes to image that, yes.
Yeah, it's pretty well mapped out between the lunar orbiters and the Apollo missions in the 60s and 70s, and then various more recent follow-ups. Like the Lunar Reconnaissance Orbiter has done a lot of high-res images of large parts of the moon, is currently still in orbit around there. And I know it's found a bunch of spacecraft landing sites.
That was the Indian space station or space agency, right?
The one I'm talking about isn't. I want to say that. Yeah, the Indian Space Agency also sent an orbiter to Moon several years back. I don't recall the details of that mission,
Yeah.
but there've been a bunch of missions by other countries also. Like China sent some orbiters and 2 landers. Japanese have sent an orbiter.
All right. So David, I have one final question for you, and we've kind of touched a little bit on it, I think. Randy Warren in the chat asked, what is the game plan here? Scientific understanding, exploration, colonization, exploitation of our solar system? Where do you see essentially humanity progressing off the Earth?
Well, wow, that's a good question. That's a big question. So where should we go versus where are we going to go? I think ultimately, I think we should be going to Mars. I have a feeling, this is just a gut feeling, that SpaceX is sort of gonna push the envelope on that, and NASA is going to get on board simply because they don't want to be left behind. Right now, NASA's plan is to go to the moon, and this time to stay, as they continuously tell us. So here's the deal. Here's what I foresee. When we built the International Space Station, and before that, it was going to be the Space Station Freedom. The idea was we need to build the space station. Well, we need a space shuttle so that we can build a space station, so that we have a staging area for all of our moon missions, and then a staging area for all of our Mars missions. That was the plan. And we were gonna, mine for fuel on the moon, and we were going to, build our colonies on Mars and so on. But in fact, because NASA's budget is so small, and because there's just no political will to do this sort of thing, we built the space station. We got the shuttle to build the space station, and we had a space station to justify the shuttle, and that was it. And that's where it died. And no part of the Artemis program today to go to the moon calls for use of the International Space Station. In fact, we need to build another space station, they say, essentially around the moon, called Gateway. I sound very jaded about all this because we've gone down this road so many times. Ultimately, what I see happening is, if in fact we do return to the moon, that's it forever, or that's it for our lifetime, and probably, definitely that's it for our lifetime, because it's going to be such an expensive endeavor that you're not going to Mars after that. And for all of our talk about building, essentially gas stations on the moon for, rocket fuel or whatever, we don't have the technology to fill a Dasani water bottle with liquid from the moon. Like that's far off technology, and that's not something that is going to easily be overcome. And I'll add to that the common argument, well, we need to go to the moon and we learn the lessons there, and then we go to Mars. That's sort of a specious argument, because because 95% of the lessons that you learn on the moon have to be relearned on Mars. The regolith is different. The natural resources are different. Mars has an atmosphere. Everything has to be relearned. And if everything has to be relearned anyway, why are we wasting our time on the moon? Let's just go to Mars. That's the next natural destination. And if we don't get mired on the moon, we can do it. So most likely, and look, this is a best most likely. This isn't terrible. Most likely is we end up having a little moon base up there, and that'd be kind of cool. But the wild card here is we basically get a free Apollo program out of companies like SpaceX and Blue Origin. So if these, men and women push the envelope and say, well, we can kind of just do this on our own, I think priorities at NASA will shift, and that would be an interesting thing indeed. So that's the wild card. The safe bet is moon base. Probably the safest bet of all is we end up staying in low Earth orbit, which is a sad thing to say, but that's what history tells us is going to happen next. As anything beyond Mars is outside of the lifetimes of our grandchildren, I would imagine, simply because in the Jovian system, you're going to be, I guess maybe you could go to Ganymede or Callisto. You're certainly not going to Europa or Io, though that might be an interesting trip. And then, beyond that, I mean, it's cryogenic temperatures on Titan, so I don't know that that would be a hospitable place. But you know what? I really like The Expanse. I think it's a great show, and hopefully we'll get in the asteroid belt too. So
yeah, one of the things that I think is that really needs to be part of the conversation now, but I think is going to essentially force the issue is what is the relationship between corporate exploration and national exploration? And for me, whoever wins that debate, I think is really going to shift the timetables and also the destinations. For instance, I think asteroid mining will become much more of a priority if corporations are taking the lead to sort of exploit those natural resources than if, say, nations took the lead. But again, that is a far-reaching conversation, and we've been at this for a little bit. So I would like to thank you again for coming and speaking with us today. And it's a fascinating subject, fascinating talk, and I will definitely be looking into getting your book and reading that, because I am curious how all of those folks that you mentioned in your subtitle are related to the Europa exploration. So if folks would like to, again, express your appreciation in the chat, I will sign off.
thank you all very much.
Thank you again. All right, folks, I'm signing off. And well, I will plug the second or the last event, the last evening under the stars, is in 2 weeks. Hopefully will not be rained out. And this will be posted onto YouTube at some point in the next couple of days. All right. Take it easy.